Okay, so last lecture of the course, for once not in the morning, which is great, so we can all be slightly less sleepy. So today we'll do many things to try to finish what I want to say. So first we will we will finish the proof of the theorem I stated on the automorphisms of the unit disk. Then we will talk about, I will explain or prove to you why Lagrange inversion works the way you were explained that it works in the tutorial, following the first homework. And then I will say something about the Riemann hypothesis. I will not prove it, okay? So, let's start with the automorphisms of the unit disk. Let's finish this chapter. So we had the following theorem that said that the automorphism, so any f in the automorphism group of the unit disk is of the following form. So it's f of z, and then a rotation times this phi a of z, sometimes a minus z, 1 minus a bar z, where a is a complex number in the disk, so of absolute value less than 1, and theta is, if you want a real number, but let's put it in 0 to 2 pi for reasons of periodicity. So any automorphism is of this form, and we checked last time that actually any such f is an automorphism. So these are precisely the automorphisms of the unit disk. Okay? So I could have written that automorphism of D is the set of all such f. Okay, so now let's see how we can prove it. So you know what we will use, right? What is the idea? What is the strong result we want to use? Schwarz lemma. And how do we apply it? This is the question. So now let's do a proof. How do we apply it? And to what function?
We try to compose f with some function that has a 0 to 0.
Exactly. Yeah, because Schwarz lemma applies to functions that maps 0 to 0. So we go from the unit disk to the unit disk and 0 to 0. So what should this be? Okay? So what we want to show is we suppose that f is an automorphism, right? Which means that it is bijective on the unit disk in particular. Okay? So suppose f is in this automorphism group D. Then in particular it is surjective, right?
Yeah.
So we can say that there exists an A in D such that f of A is 0. And then we also recall that phi of 0 is A and phi of A is 0, but here we use this. Okay, so phi A of 0 is A. We also use this. And it means that if we compose these two together, we can send here 0 using phi A. We can send it to A, and using f, we can send A back to 0. So what we should consider is f phi A composed. F composed by A. Exactly. So f composed with phi A of 0 is equal to 0. And of course, this is a map from the unit disk to the unit disk. Okay? So, and f composed with phi A is from the unit disk to the unit disk. So we can apply Schwarz lemma. And what does the lemma say? So, by Schwarz lemma, we get we can have two possible conclusions, right? So we can say that the absolute value of this in the point z, for every point z in the disk, is less than or equal to the absolute value of z. Or we can have the other conclusion about the derivative in 0. Okay? And in this time, if you remember this from the last lecture, so in this time, let's call this g, by the way, so I don't have to write this all the time. So F composed with phi A is G. So by Schwartz lemma, you get that absolute value of G prime of 0 is less than or equal to 1, if you remember. Okay? This was number 2 in our list of conclusions. But then also, so similarly, so G here is an automorphism, which in particular means that G inverse is also defined and it's also an automorphism, because this automorphism group is a group. Okay, so the inverse is also in it. So similarly, we can also apply this to, we can apply Schwartz lemma to G inverse. And G inverse prime of 0 has absolute value less than or equal to 1. Okay? But this implies that actually G prime of 0 must be equal to 1. Because you see, as you remember, the derivative of the inverse is 1 over G prime in the appropriate point, which will still be 0. So it implies this. This was the key step of the argument. Everybody got here. And then we remember the third part of Schwartz lemma, which said that if we have equality in 1 or 2, so this is equality in the second point, then actually the function is a rotation, up to rotation, it is just the identity. So this means, again by Schwartz, that G of Z is equal to e to the I theta, or let me write lambda Z, where absolute value of lambda is 1, so it's a complex number. So it is almost the identity. So in other words, what we have is that this thing here is e to the I theta times Z. What is going on? Yeah, sorry. I didn't hear. This is correct? Okay. So this means that f of z is equal to e to the I theta phi a of z. By the way, of course, if you remember the notation, this is what I call phi a of z. I realized I didn't recall this today. Okay, and this finishes the proof. Because so this is for some data that we can choose between 0 and 2 pi.
CA squared equal 1? Yes.
Sorry, CA squared what?
CA composed with CA is the
identity? Yeah.
Okay.
CA composed with phi. We saw this last time.
Okay.
But it's its own inverse.
Yeah. Okay. Yeah.
Okay, so this proves that if we have an automorphism, we can write it on this form. So you see, it's actually very easy proof. Yeah. It's quite a strong theorem, to be honest. I mean, it's quite impressive, but with Schwartz lemma, you can prove this very quickly. So this is the kind of thing that is very good to be able to do. Okay, some final remarks on this automorphism, unless you have questions on this proof. So the final remarks is that we can also do it for other domains. So we can consider an automorphism group of omega, where omega is something else that can be mapped onto the unit disk. So a remark can also deduce results for example, the automorphism group of H, where H is the standard notation for the upper half plane, okay? The imaginary part is strictly positive. So we can also, or any other domain that you can map onto the unit disk. But let's take this as an example. So then, in fact, we have a following claim that, okay, how actually, I can ask you maybe. So how is the automorphism group of H related to the automorphism group of the disk?
Conjugation. You we conjugate the first group with the holomorphic map that makes H to the disk.
So that is a map from one to the other.
What?
So that is a map from automorphism group here to the automorphism group of D.
Yeah, which associate to each automorphism of the disk. Phi composed with F composed with phi minus 1.
But actually this map, yeah, you're correct, but actually this map is an isomorphism.
Yeah.
Yeah. So actually they're isomorphism, and you gave the isomorphism.
Yeah.
Yeah, so that's very good. So actually these ones are even isomorphic. And the explicit isomorphism, just as you said, is given by considering first of all you take F that maps H to D, that sends Z to Z minus I over Z plus I, right? Yes. And then you consider G, which is the inverse. Okay, so F inverse, which takes D to H. And then you recall how you compute inverses, so why not just do it instead of trying to remember. So this one corresponds to the matrix 1 minus I, 1, I, right? And so this means that the inverse here should correspond to, so if I take the inverse, so 1 minus I, 1, inverse, up to a constant, we forget, you remember this 1 over determinant. So this is the same as you interchange these and you take minus on these, right? So I always have to try to remember. So it's I, minus 1, 1. So it corresponds to this. So it means what I should write here is W goes to I times W plus 1 over minus W plus 1, which looks much more beautiful if you write it like that. Okay? So this should be the inverse. And then, just as you said, we take conjugation. So now we get that. Okay, so now we get this explicit isomorphism, taking, so if you have phi here, you take it to, so an automorphism of H, so it means that I start in H, okay, and then I want to go using F, I want to go into D, then I want to use phi to go again into D, then I want to go back to H, and this I use F inverse, which is G. So I should consider this to be equal to F inverse. So what I do is F inverse by F. So this is my explicit isomorphism, okay? And the exercise, because if I want to say anything about the Riemann hypothesis, this is an exercise. Show that this is a group isomorphism. Okay. And isomorphism, remember that these are bi-holomorphic, okay? So they are bijective holomorphic map. This is a bijective holomorphic map, and its inverse is holomorphic. This is what it means to be isomorphic. And the group is, of course, with respect to composition. Okay, so that's what I wanted to say about automorphisms right now. Having said all that, I think I trust you to be able to deduce all the necessary variations of this when I throw some problems onto you. Maybe in homework 5. Okay? So I showed you now for H, but you can do, of course, this for other things, for example, and you can deduce various things. How to use Schweitz lemma, how to use Möbius transforms to put yourself in the right situation to apply Schweitz lemma. Okay? questions on that? Otherwise, I think I will maybe erase everything, because now I will start with Lagrange inversion. Okay. So now I want you to start remembering this Lagrange inversion business. And I mean, I remember very vividly, it wasn't long ago, that you were all very frustrated with this bonus exercise, saying it's not possible, and so on. Or it's very hard, and how do you do it? And indeed, I mean, it was the kind of exercise that I don't know how you should think of solving it, to be honest. I mean, it was way above, clearly the hardest exercise on all the homework problems, right? But now we have come to the end of the course, and now we have all the necessary tools to give a very simple proof of why it works in this way. So now, and since I gave you this bonus problem, I think it is a nice thing to prove to you why it works before the end of the course. So the next topic is Lagrange inversion with an exclamation mark. Okay, so what is it about? So Lagrange inversion is, so it continues also naturally the topic that we talked about the past days, right? That we talked about locally invertible holomorphic functions. So we said that a function is has a local inverse if and only if the derivative in that point is non-zero. So we said this. So yeah, so let's recall it. Let's put it on the board. So locally invertible at z0 if and only if f prime of z0 is non-zero. And f is, of course, an analytic function. This is assumed. Not always writing this. Okay, and now let G leave a local inverse to f. So where G is defined in a small neighborhood with my standard MTH, meaning neighborhood, of W0, which is f, so the image of Z0. This is where the local inverse would be defined. And now the question was, so f is analytic, so it has a power series expansion. It has now, assuming this condition, a local inverse, which is also analytic, and it has a power series expansion. And so if we want to describe somehow what this local inverse is, one way to do it is if we could find the power series expansion. So the question is, how do you get the coefficients in the power series expansion of this G? I mean, so let me write, so G is analytic, so we can write G of W. So I use now W because I think I am in the image space where the variables are called W. So so around this point, W0, we have here that it is of the following form. Sorry. And so on. And we want to find these AKs, these coefficients. And how do we do it? So how do we find AK? This is now the question. And you know how to do it, I think, depending on how much you remember, but you were told during the tutorial some kind of algorithm of how to do it. Who remembers how to do it, by the way? No? Good. Then I'll remind you today. So, I mean, it's hard to remember when you don't know the proof behind also, for sure. So now, to do this, so first note, so first we consider this, we multiply G of W that we're interested in. We multiply it by W minus W0. And then this is equal to A1 W0 plus 2A2 and so on. So we get that this is equal to B1. Let me just rewrite it like this, where Bn is n times the thing we are interested in. Yes? No? Sorry, G prime. Yeah. All right. I forgot the prime. No, so G prime is equal to this. So we look at this thing, that's G prime, and we say that, okay, of course, now if we can find the Bn's, we can find the An's. So we now are interested in this. And then, so by Cauchy, so Cauchy's formula says that the coefficients, so actually, the coefficients, they are the nth derivative divided by n factorial, right? So by this is equal to 1 over 2 pi I, the integral over some gamma. I will tell you what gamma has to be. So it has to be winding number 1 times this. Okay, so let's call this, by the way, let's call this something. Let's call this H. Otherwise it's so long to write. Okay, that's acceptable, I hope. So the integral of HW, so it's equal to this, W, where gamma is any path with winding number, okay, satisfies this. So the winding number has to be 1. This is clear, I hope. But you should remember this. Otherwise, you'd have to modify the formula. So we have this. And now we want to apply this to a suitable gamma to get something we want. And what gamma do we want to take? Well, so I have a following claim. But first I consider C is a small circle around Z0 with radius epsilon. Of course, a very small radius. Okay. So this is C. And then I consider gamma of t to be F composed with C of t. So I look at the image. So F was my function that I started with, right? So this is where F comes in again. So if I look at the image of this circle, I'm looking at the image path, the image cycle, okay, under F. So now the question is, what happens to a circle when you map it with just any analytic map? Okay, so we know if it was a Möbius transformation, it would be another circle or a line. But now it's not so simple, because now it's just any analytic map, so we don't know a priori what's happening. So this thing here, in the picture, so this thing is mapped under F. So inside, all we know is inside here is Z0, and somewhere here we have W0. And it is mapped to something that does whatever it does. I don't know what it does. It does this. Okay? It can be mapped to something very wild in general. The images are very complicated. And they typically look something like this, actually. Even if you take an image under a polynomial, say. They look quite wild. You can try this. So you have this to be the image curve. But there is something maybe that you can see in this picture that I tried to get into the picture deliberately. There is something that is preserved here. What is the winding number around W0? It is 1. And is this an accident? What is the question? Of course, I'm asking you because it's not. Right. So this is not an accident. So here you see that the winding number, let me write this. Yeah, so the winding number here of f of c in W0 is still equal to 1. Okay, so this is we claim. Okay, so of course here, I mean, I don't have to write you a parameterization of this. So what is the reason for this? Try to get maybe with another color. Green is probably a nice color. Okay, so explanation. Okay, so what you do is that you take the disk, I mean this circle you take so small, so that f of z minus W0 has a simple 0 inside this circle C. Okay, and you can do that because zeros are isolated. Now we're doing something that we did before. And then you get that this winding number of this image of C in W0. So now we just use the definition of winding number, which is equal to this f of C dw over W minus W0. I don't know why I put the parentheses. Okay, so this you remember. Okay, but so this, now we have this integral, and we can just, to understand what it does, we can just write this on parametric form, like a real parameterized integral. So it goes from 0 to 2 pi, and it goes from f of c of t times c prime of t divided by f prime. Yeah, f prime is this right? Divided by f of c of t. Too many parentheses here, maybe. Minus W0. Okay, I feel like I should not write out the parentheses or it will be unbearable. So let me write it this way. F prime of c of t. F of c of t. This is better. Minus. Why minus? Is there minus?
Minus W0.
Oh, minus W0. Oh, okay. Yeah. Okay. I thought you meant here's something else. Okay. Thank you. Minus W0. Okay. And dt. That's good. So you have this. We all agree? Now, what is this? This is the question. So now this is equal to, so I mean, I'm just playing back and forth just to recognize these things. So now if I wrote this as an integral over the curve C instead, what would it be? Okay, 1 over 2 pi I is always the same. So I can put C in here. And then I could say that it would be f prime of z over f of z minus W0 dz. Okay, so it's the integral over C. But now, what is this? Well, now we have this fabulous argument principle, no? Which says that this is sum of n of over this C of the AK over all K, where AK are zeros of F inside C.
F minus omega 2.
Sorry?
F minus omega 2. The C.
Oh, yeah, yes. Sorry. Like this. Thank you. Inside C.
Why the boundary of the first integral is from 0 to 2 pi?
Because C is parameterized. So T here, the parameter, goes from 0 to 2 pi because it's the circle that goes around.
Yes, but this is a parameterization for C or for
It's for C.
F circle C?
I mean, it's the parameterization for C, and then when you take the image, you use the same parameter T, and you just take F of C of T. No? So it's F of C of T also goes for T from 0 to 2 pi, by definition. Okay, so these are zeros, but I assume I wrote it here. This has a simple 0 inside C, and this is the only 0. And zeros are isolated, so I can say that. So this is equal to simply okay, this winding number, which is what did I want to say again? Which is equal to 1. Yeah, this is what I wanted. So I want to show it 1. This is what I wanted to show. So now this kind of, I mean, this is a little bit almost unnecessarily long, you know. You can just maybe skip one of these steps if you see immediately, for example, that that thing is equal to this or something. And then you just have to say, I chose everything, I set up the problem so that the C was so small that it only contained 1 0. Okay? And the reason, by the way, that this is a simple 0, so 0 for the 1, why is that? Why did I write this, that it's a simple 0? Just as a small test. Exactly. If this was a double or triple, it would not be locally invertible. Okay? Because then it would cover, any small neighborhood would cover n times another neighborhood, it would not be bijective. Or the most simple explanation, f prime would not be non-zero. It would be there. Okay, so this is the explanation for that. And now, okay, so by the claim, so n of this gamma around W0 is equal to 1, so we can apply this formula, okay? So by this star thing here, this is star, we continue our computation. So, you know, we had to do a little pause here to see that we could apply it to this gamma. Now we apply this formula Bn is equal to the 1 over 2 pi I, the integral, and so the integral of that, okay, which is equal to the integral from 0 to 2 pi. So I write it in parametric form. So h of gamma of t over gamma of t minus w0 to the n plus 1 times gamma prime of t dt. So it's equal to this by definition. And then we continue our computation on this page here. Okay, so now comes the maybe slightly, the only slightly non-obvious equality in this sequence. So this is equal to 1 over 2 pi I, the integral from 0 to 2 pi, and then of f of c of t minus w0 divided by f, this is unbearable, let me write it, f composed with c of t minus w0 over f composed with c of t minus w0 to the power n plus 1 times f prime of c of t over f prime of c of t dt. Okay, so it's equal to this. I think it's still readable, no? Okay, why is it equal to this? Small justification again. Personally, when I work, I like doing this sort of the main calculation, and then in different colors I use the maybe to justify it. So this h of gamma of t, so this is by definition, so gamma of t, so g prime of gamma of t. This was the definition of h, right? Here I had h of gamma of t. So it's equal to that, which is then equal to, if I put in what gamma is, it is equal to f of c of t minus w0. Okay, so I have this, and then times g prime of f of c of t, okay, which is equal to, if you now use again the definition of this, g prime c of t minus w0 divided by f prime of c of t. What have I used here? Using that g is the local inverse, and then I use the derivative of the inverse, right? So g prime of x is equal to 1 over f prime of g of x, right? So use this formula, and this means that g prime of f of c of t is equal to 1 over f prime of g of f of c of t, which is equal to 1 over f prime of c of t. Okay, I hope you can read this. So this is supposed to be the justification for all of that. Is it okay? Okay.
Then we should have an c prime of t also when we compute the derivative of gamma of t.
Yeah. What? So now here, where?
No, this equality.
Gamma prime. Ah yes, I didn't put what is gamma prime of t. Yeah. Should we? Should we? So let's see. Okay, I'm sure this is supposed to be right somehow, but it's hard to see. So 1 over f prime of t. So
gamma prime is f prime.
Yep.
The one with the top and the down.
But there is one derivative too.
so it's
There is a c prime, and when you compute the gamma prime, there is a c prime.
yeah.
When you compute the derivative of g, there is also a c prime.
So there's a c prime here, you're saying, or no? You're saying it cancels.
Yeah.
It cancels. Okay, you're saying it cancels. Yeah. Okay. Let's proceed.
I think they will not cancel because it is g prime of gamma of t. It's not g of gamma of t prime. I mean in h of gamma of t.
So gamma prime of, yeah, it's a mess of this. So we have this lower thing is bad, at least that much we know. H of gamma of t is 1 over. So we're saying that gamma prime of t is equals to, yeah, f prime of c, where So this is equal to,
This I think we forgot,
the C prime of T.
yes, from
Yeah.
the down here, because
Mhm.
G prime of X is
Yeah, this one.
that one. But we differentiate with T. With T. And that one we forget somehow.
Yeah, I think we forgot the C prime of T. Okay, is it better? Okay, thank you. So let's continue then. The next step after this. So this was just for justification. Now we continue this. What is this equal to? Okay, so we of course have things that cancel. So this one cancels to this. So it is equal to the 1 over 2 pi I integral from 0 to 2 pi of this over this, but I can write this as dt. But let me write it. 1 over f of c of t to the power n c prime of t dt, which is equal, and then we again get rid of this c prime here now when we go back to saying that this is equal to 1 over c times dz over f of z minus w0 to the power n. Okay? This is good. Yeah, I'm very happy you're really following the attention to detailing. It's very good. Thank you. So we have this, and this is the sort of key step here that we have. And now we take a step back. Now take a step back. Okay, so we want to see how can we continue this computation basically and get something meaningful out of this. And then what we do is that we consider this f of z minus w0, so this function here. We can write it equal to some a1 z minus z0 Okay, so we write it like this, where a1 is not 0. Okay, and because the 0 is of order 1, okay, because it was locally invertible, 0 had to be of order 1. And then we consider some other function, let's call it maybe j, because g is already taken and h is already taken. So let's call it j of z, which is f of z minus w0 over z minus z0. So let's define this. So here, we should note that j of z0 is equal to a1, which is not 0. So this is important. So of course I don't have to write down what this is, you can just do it in your head. And now, because it's non-zero, we can look at 1 over j. We can even look actually at 1 over j to some power. So now we can consider 1 over j to jz to the k. Okay, and this is equal to, so we write this using this notation. Okay, and so on. So this k parenthesis indicates that it corresponds to this k simply. Okay, is this good? And this has positive radius of convergence, since basically the thing I'm dividing with is not 0. Okay. So because this happens. So now get back to our computation. Back to the computation. So we stopped here. Let's call this double star. So now we have the double star is equal to, so now what I did is that I took this thing here up to, you know, a factor of z minus z0. I wrote this thing as a convergent power series in a small neighborhood. So this star is equal to 1 over 2 pi I, the integral over c from z minus z0 to the n. So we were computing Bn, right? Yeah, so by, let me write it like that. So this coefficient Bn, which was n times what we wanted from the beginning, was equal to this divided by f of z minus w0 to the n. Okay, so I just multiplied by 1. But now, of course, this is j. So this is equal to 1 over 2 pi I integral e of j of z times 1 over z minus z0 to the n dz. Okay, so it's equal to this. And now to continue, we see that this is the, so now we will have to justify again, as usual. If we want to be completely rigorous, we should justify to interchange the integration and sum.
J to the n.
J to the n, yes. 1 over, yes. 1 over. 1 over j to z to the n. Okay. That's what it is. Thank you. And this is this one to the n. So this is equal to the integral, always this 1 over 2 pi I. It's like the thing that haunts you in complex analysis. You spend 8 years of your life writing this in total. Okay, sum of all these, so m greater than or equal to 0, Cm corresponding to the power n that they took, so these coefficients, and then times this okay. Yeah, so I wanted to say directly, let me write directly that I interchange the order of the sum and integration. This is what we want to do. Actually, then I want to put the 1 over 2 pi I in here. And I want to say that this is z minus z0 to the power m minus n times dz. Okay, help me out here now. Now I can no longer clearly see what I wrote in my notes, so it looks like it's maybe this, but now we have to check it. Is this what it says? So I have, first of all, the sum, and then I just have these z minus z0 to certain powers. And I had, to the nth power. Okay, so so this is bullshit, no? It is. Okay. So we have this. And I can write it, so what I had in my notes was probably, I can write it like that, and then I can add +1 here. So I can do that. And this is good because, now what does this integral equal to? Okay, so let's call this integral I. So it depends on n, so let's call it Im. N was fixed, so Im. So now Im, so this integral, it is equal to what, actually? Let me add.
0 if n minus n plus 1.
0 if, yeah, or something like that.
Yes, and 1.
And IM is equal to 1. Very good. If M is equal to M. Okay? So this is, of course, because when it equals to the integral of dz over z minus z0 times 1 over 2 pi I, which is 1. This is the logarithmic classic thing we've seen many times. Okay? So what does this mean? So because of this means that when I continue from up there, then this is equal to what? It's actually equal to simply, I mean, all of these are multiplied by 0 except when it is 1, when m is equal to n minus 1. So it is equal to c n minus 1 n. It's equal to this coefficient. Okay, so what we get is that Bn is equal to n times what we were interested in, which is equal to c n minus 1 n. And this means that An is equal to 1 over n Cn minus 1 n. So these are the coefficients of the inverse. I hope you recognize this from what you were told in the tutorial maybe. But actually, I mean, since I don't think you particularly seem to remember this very freshly, let's do the bonus exercise again. It's very quick, anyway. So let's do a bonus exercise. So the example is if we take f of z is z into minus z, and we look in a neighborhood of 0. Let's just do that for an exercise. Okay? Z0 equals 0. So this W0 is also equal to 0. So this is now our application. Then we get that this j thing, so 1 over j, is bar k is this, which is equal to this, which is equal to e to the minus kz. Okay? Sorry, e to the minus e to the kz, yeah. E to the kz, which is equal to 1 plus kz over 1 factorial plus kz squared over 2 factorial, and so on. So this means that now we want to read off what is this Cn minus 1 of n, right? So we want to read off this coefficient. And what is it? So the general coefficient here is, of course, n to the power n over n factorial to n. Okay? So it's equal to this. So it means that the n minus the coefficient for n minus 1 here is the one we're looking for, right? So this is equal to n to the n minus 1. I mean, sorry, I might as well write it like this. Okay?
N, okay.
K, yeah, of course, K. K or n or whatever. I mean, the n minus first.
No, the n are everywhere except
Okay. Yeah, sorry.
and n, yeah.
Yeah.
N.
Sorry. Okay, now I see it. Okay, so we have this. But still, if we take, okay, so what what was confusing me is that if we take Cn minus 1 with n in parentheses, then the k is n.
Yeah.
Okay, so the k is n. So this is equal to, imagine k is n. That's equal to this over n minus 1 factorial. Okay, but this is not what we wanted, because what we wanted was an, which was 1 over n times this. Okay, which implies that an is equal to 1 over n times that, which is n to n minus 1 over n factorial. Okay, and so these are the coefficients. So what it means is that precisely, yeah, it deserves a new board. Okay, so J of W is sum of n factorial Wn defines a local inverse to z e to the minus z at W equals f of 0 equals 0, okay? W equals 0. So this is the local inverse. This is not a factorial, but it is cool. Okay, and this, by the way, you can see that if you take the radius of convergence, you can easily compute it. This is with this simple computation. Okay, and so the radius of convergence equal to this. So you get the local inverse around W equals 0 to this thing here, and it's convergent at least when R equals 1 when we radius of convergence is this. Yeah, I'm very disappointed you didn't all find that solution. Precisely because we could. Okay, very good. And we still have a good chunk of time actually to discuss the final part. I mean, are you satisfied with this? Yeah. So you have a good chunk of time discussing the Riemann Zeta-Function, the gamma function, the infinite products, and at the very end, I will write down the Riemann hypothesis. Okay. So all of this will, of course, be fairly sketchy. You know, you cannot. So it all started with this paper in 1859 by Riemann. This paper looks like this. It's in German. You might think I speak German, but I don't really. So this paper in 1859, it was fairly long ago. This is where, so it's called, the English title would be On the Number of Primes Below a Given Magnitude. So from 1859. And Riemann, he tried to understand basically how many primes are there among the first 1 trillion digits, or whatever number you choose, right? Among the first k digits, how many primes are there? And so he started considering all these functions, and then they got their life of their own. And so this last section is really about this promise I gave to you in the first lecture. I said in the motivation that complex analysis is everywhere. So I have shown you, I have discussed mostly complex geometry if I discussed anything, right? Because, I haven't discussed it much either, but that's my field of research. But it's really something that appears also a lot in number theory. So let's just try to sketch a little bit about that. So, infinite product gamma and zeta functions. Yeah, I mean, it's kind of a miracle, really, that complex analysis comes in so much in so many different fields. Like these, you know, you have in physics, you have this, I don't know if you ever thought of this Schrödinger equation, if any one of you has heard of this. Why is there, you know, a complex number I coming in there? You want to describe a universe and then there's an I. You know, where did it come from? What happened? So complex analysis really is there somehow in a deeper way than you can easily understand, at least. And also in number theory, you have all these, you're looking at the primes. I mean, you're looking at the numbers like 2, 3, 5, and so on. And somehow you want to use complex analysis to say something fundamental of primes. The most famous and fundamental theorem in number theory, but probably in all of mathematics, is about a meromorphic function. And we use it to study primes, which is also kind of crazy, if you think about it, right? And so this was formulated in 1859, this Riemann hypothesis I will get to, and it's still unsolved. And if you solve it, you get $1 million. Yes, okay, so basically brief remarks on complex analysis applications in number theory. Could be a subtitle to this. So many important analytic functions can be written as infinite products. So this is why I have this part here. So I will use this as an excuse to say something for 2 minutes about infinite products soon. So okay, so yeah, let me write it. So many special analytic functions can be viewed as infinite products that you will see in a second. So the main player here is the Riemann Zeta-Function. And it's defined in the following way. So it's defined as the sum from n equals 1 to infinity of 1 over n to the power s, where s is a complex number. And so now I'm using, I can prove to you that I'm using the original notation from 1859. This is why I'm all of a sudden calling it s, okay? So s is sigma plus I times t. So this is, I mean, nowadays this has gotten a life of its own, so people would just write sigma and everybody should know what it is, if you're in this field, right? Studying the zeta function. So, okay, this is the famous zeta function. It satisfies this, but it satisfies this for appropriate s, right? Because you need this to be convergent. Okay, so this is defined when this real part of s, which is sigma, is greater than 1. Because then this converges. So this is how it was initially studied. We say, okay, let's study this series. Okay, for some reason, we want to study this series. Bernard Riemann had this amazing idea. And of course, I want to study it when it converges. But then, eventually, other people came along and we realized you can actually extend this sum that is convergent in this half plane. So it's convergent here. Okay, so this is 1. But you can actually extend it to something in the whole plane. Okay. So let me just write this down. So this defines an analytic function when sigma is greater than or equal to sigma 0 greater than 1. Why is this? Just as a little recap of the course that we have gone through as well. So when we have power series, this was a long time ago, but we had this M test, right? The Weierstrass M test that was very useful to use back then. So what we do is we say that, of course, this kind of S, so this is less than or equal to in absolute value. Yeah, okay. So we compare this to the following, to the sum. So we compare this to the sum of 1 over n to the sigma, okay? Because the absolute value of the former one is measured by this, okay? So this one is finite if sigma is greater than 1, okay? And this means that this sum of 1 over n to the s actually converges uniformly whenever sigma is greater than some sigma 0 greater than 1. So on some compact, it converges uniformly. And then the M test. Okay, then we have that all the partial sums converge uniformly to something. And then we saw that if we have this uniform convergence, then actually we get an analytic function in the end by the M test. So the M test will imply that it's analytic. I mean, in particular, it's continuous, but it will even be differentiable. Okay? So it defines an analytic function on this half plane. Real part greater than or equal to 1. So this is the first part in the sketch here that I'm trying to do. But now we can actually extend this function to the whole complex plane. Okay? And now the only question is how many pages I should skip in doing this, how many details I should give and how many details I should skip. But I will sketch something at the very least. So this is where the gamma function comes in. So to extend it, what we want to do, the idea is very simple actually. So the idea is that if you have something that does not converge, that does not make sense except on this set, then you show that actually on this set, on this half plane here, it equals to something else that makes sense everywhere. And then you study instead this other object that makes sense everywhere.
It means it's
Does
a
that make sense?
restriction of something defined everywhere, or what?
Yeah. I mean, so you have some function defined everywhere that is equal to this sum on this set.
Yeah.
And then this extension, this new thing, is what we want to call the Riemann Zeta-Function. Okay? And so this object that we can extend, in order to formulate it, I need to introduce also the gamma function, because this object is defined as 1 over the gamma function times an integral. Okay? And the gamma function is very important in itself, by the way, in number theory. So consider the gamma function. Yeah, so I think most people would agree that it's considered, I mean, it should be part of the general education to know at least about the gamma function, actually, what it does. So the gamma function is the special function. So, we don't really have a standard expression like f of z is z to the e minus z log sine, something like that. But it's an integral. So it's 0 to infinity of x to the power s, e to the minus x, dx divided by x. So I write it a little bit weirdly like this. You could, of course, write x to the s minus 1 if you want. Okay? So I write it like this. So this is the gamma function, which is this integral. And, okay, the claim is the following. The claim is that this gamma of s is analytic, well, is it everywhere? Analytic in the real part of s is greater than 0. Okay, so now, from now, I'm not going to justify in detail all of these claims because it's a huge, collection of literature. where these things converge, where are the zeros, where are the poles. Okay, this is essentially what these unsolved problems are about. But this is analytic on the positive half plane. Okay, and moreover, we have the following identity. So this is maybe the most fundamental identity about the gamma function. And the proof of this identity is by integration by parts. Okay, so this is very simple. Okay, so this you can do. You just take this integral I gave you and you do one simple integration by parts and you get this. Okay? Now, this is extremely useful because we have that, and also we have, you can think about what is gamma of 1 while I erase this word. Gamma of 1 is 0? No.
No, the gamma function is an extension for the
Yeah, but it's not defined in 0, because we said that the real part should be strictly higher than 0.
So gamma of 1 is what? So gamma of 1 is the integral from 0 to infinity of e to the minus x.
It's 1.
Yes, 1. Yes. Yeah. It's 1.
Yeah.
Okay, so gamma of 1 is 1. And this implies that in particular now if n is some natural number, so gamma of n plus 1
N factorial.
Absolutely. It's n factorial. So this is equal to n times n minus 1, gamma of n minus 1, which is equal to, in the end, n factorial, like you said.
This is s plus 1, right? Gamma s plus 1 is s plus 1 gamma s?
No. It's correct like this, no? I think. And then I get this and that and everything.
Yes, okay.
Yeah. And yeah, and so as some of you at least seem to have already known, what this means is that on the natural numbers, this gamma function is equal to the factorial. And so it's an analytic function on the whole positive half plane that in the natural numbers is equal to the factorial. So it's an analytic extension of the factorial function. Okay? So this is an analytic extension of the factorial. Okay? Just for your general culture. And now we can continue using this in order to define the gamma function more generally. So for now, the gamma function is defined on a positive half plane. But actually, we can use this amazing identity here to define it as a meromorphic function on the whole of C. And how do we do that? Well, we say that gamma of S is equal to this. Okay? But we say that this should hold also for real part of S greater than minus 1. Okay? And then this has a simple pole at S equals 0. So this is now a meromorphic function. Okay, so meromorphic function on this half plane that is now become slightly larger, right? So we can now go to minus 1. But now we've got a pole in S equals 0. Which is fine, because we know how to deal with simple poles. Okay? So we're not too upset that it has a pole. Then we can continue. Yeah, we can compute the residue, by the way, of this pole, if you want. So the residue at S equals 0 of gamma of S is equal to gamma of 1, which is equal to 1. So you can check this if you want. Then you repeat the process. And once you repeat, you get that gamma of S is equal to the gamma of S plus 2 divided by S times S plus 1. And this is now okay when the real part of S is greater than minus 2. I mean, did you all understand why I'm saying greater than minus 1, greater than minus 2? It was because gamma of S was defined on a positive half plane, so now if I have gamma of S plus 2, I can define it up to minus 2. And it's analytic, and it has 2 poles. So now it has also a pole in S equals minus 1. Okay, and you can compute the residue. So fact, so by induction, can define gamma of S to be a meromorphic function on all of C with simple poles. I mean, of course, I'm going to continue S plus 1, S plus 2, S plus 3. So with simple poles, when S equals 0, minus 1, minus 2, minus 3, and so on. Okay, and the residue, just for fun, essentially, the residue of S in minus n is equal to minus 1 to the n over n factorial. Okay, and this is true for n equals 0, 1, 2, and so on. So all the natural numbers. So now, by using this formula over there, and using, that's valid for S greater than 1, we could successively define it to make it into a meromorphic function defined on all of C. Okay, so this is very clever by the people who came up with it. Okay. And now, let's see. So now let's get back to the zeta function. Okay, so we have the following theorem. So I have here also in my notes a sort of deduction of why this is true, which I could maybe explain later, but in order to ensure I make it to the end, let me put the theorem first. So the theorem says that for the real part of S greater than 1, so this sigma greater than 1, using Riemann's notation, then this function has a totally different expression. So it's equal to this sum that I told you in the beginning, but it's actually equal to gamma of 1 minus S over 2 pi r times some integral here over C. Yes. Okay. Minus Z S minus 1 over e to the Z minus 1 dz. Where, okay, I'll sort of hide from you what is this curve here. Okay, what is this contour C? Yeah, I could explain. I mean, if you start explaining what this C is, then you have to go into a long sort of thing. This is a special contour. This is not just any contour, but it's something special. Okay, it's something like almost like a keyhole contour. It's something like that. Okay, so C here is a special contour. Anyway, you have such a theorem, and so the remark is that this right-hand side, if we consider the right-hand side here, then we see first that, okay, first I claim that for any S, this integral along the curve, I have not told you what it is, but you can check anyway. So let's just take this as a claim for now. So this is entire, this function, okay? So it's an entire function of S, okay? Entire function in the variable S. And then you look at this gamma of 1 minus s, so this is meromorphic, so this has poles somewhere. So gamma of 1 minus s, or if you want, minus gamma of 1 minus s. So this has poles. Where does it have poles? At s equal 1 only?
All negative integers, all positive integers.
Yeah, exactly. So where did we, yeah, exactly. So gamma of s for this. So this has poles in, actually not 0, right? So s is 1, 2, or so on. Yeah, so it depends what you mean by positive, right? If is 0 a positive number or not, this is an eternal discussion.
But one is not bad because we say that the part of S is
yeah, okay, so I mean this, okay, but this function we can still make sense of, right? So if we just consider this locally, this is a true statement. Okay, and then moreover, gamma of s, sorry, zeta of s is analytic on this half-plane real part of s greater than 1. So this means that even though this gamma of 1 minus s has poles there, it has to be counterbalanced by the zeros. Okay? So we are, this one has poles, but your product does not have poles. Because the whole thing we know is analytic, because it equals to this sum by the theorem. That you can actually prove quite easily, so if you want to stay afterwards, I can show you, it's half a page, to show that this equals to that sum. Okay, so since it's analytic, it means that poles in all these natural numbers greater than 2 cancels against zeros of this integral part, okay? And so what remains, simply, so we said this one was analytic, this one had poles, but in the poles n equals 2, 3, and so on, it was counteracted by the zeros here because we knew it was analytic. So the only remaining part to look at is, as you said, on the boundary of where we know it's analytic. So when real part of s is exactly 1, well, so when s equals 1. So when s equals to 1, what do we have? Then minus gamma of 1 minus s has a simple pole. With residue 1. Okay, I hope that's true. The simple pole with residue 1. And now, the claim, so what we have shown is the following. It's a claim or a theorem, whichever you want, that the zeta function can be extended to a meromorphic function on all of C, whose only pole is at s equal 1. Okay? And just to add a little bit, so with residue 1. Okay? So this we can do. So thanks to, basically what I'm trying to sketch here is that thanks to having such an equality that, as I said, is not so hard to prove, then you can actually make sense of this as a meromorphic function. So now this is our zeta function. So we forget that we wanted it to be the sum of 1 over n to the s. For now, we say, now this is the zeta function. This is our new definition. And it's a meromorphic function on the whole plane, and it has only one pole, so it's actually quite nice, right? And we even know it's residue. Okay, now we have one more ingredient, which is nice. So, because the question is, okay, we know it's a meromorphic function, we know it has one pole, but what about the zeros? Okay? So now the question is, what about zeros of the zeta function? So then we have the so-called functional equation. People have studied this for many years, trying to solve this extremely difficult problem. And someone came up with the following statement, which is, I mean, amazing. So I think depending on who you are, you have different strengths in math. And for me, I mean, some things seem very natural, and some things like this theorem, I think I would not be likely to be the first one to prove. So something like this. Okay, so you play around with this until you understand that, that this is equal to the zeta function. Theorem, let me put theorem up here, and then write that zeta of s is equal to this. Okay, so you have some equation where you have the zeta function on both sides, by the way, but here it's of s and here it's of 1 minus s. So okay, why not? Someone fought very hard, possibly many years, his whole life, came up with this. Okay? Now, this implies something about the zeros. So this implies, so the Riemann hypothesis is about the zeros of the zeta function. But there are some trivial zeros. So look at this and try to tell me what are the trivial zeros that you can read out of this. Integers. Okay, it has trivial zeros, so think you're good, but think a little more. So okay, yeah, I remember right. Okay, so it's when this sinus of pi s over 2 is 0, but also and when simultaneously gamma of 1 minus s has no poles, right? Because if it has poles, we don't really know what is going on. I mean, these are what we want to call trivial zeros, so this cannot be called trivial if we want to see what happens with the balance between zeros and poles. And so what are these? What are these? So we get the trivial zeros, so-called trivial zeros that are odd integers.
Even.
Negative even integers, okay. That is correct. Minus 2, minus 4, minus 6, and so on. Very good. So we get these trivial zeros. And now, to the final part here. Why do we care about their zeros? And why do we care about the zeros? This is now the last part. So I cannot tell you which are all the zeros. This is what the difficult problem is about. But now, all of this is important because of the product development of this zeta function. Okay? So the interest in number theory comes from this. Interest in number theory comes from the following theorem. And this is what, this is in this paper here by Riemann, the old yellow pages from 1859. That for real part of S greater than 1 over the zeta function is equal to this infinite product n equals 1 to infinity of 1 minus 1 over Pn to the power s, okay, where P1 to Pn, I mean, the Pn's are the primes, right? So P1, P2, and so on are ascending, so this is an ascending sequence of primes. Okay, and in this lecture I assume that there are infinitely many primes, which is true, which we have known for a very long time as humanity. So you have this product. And now I should tell you just very quickly what does it mean for such a product to be convergent, okay? So I should tell you, so remark convergence of infinite series, infinite products, okay? So what does it mean for an infinite product to converge?
Limit.
There's a limit, but you know it's a bit more complicated than somehow when you have a sum. Because if you have an infinite sum and you have one term which is 0, then nothing happens. But if you have an infinite product and just one factor is 0, then the whole thing is 0. So everything collapses, you know, and we have these small problems. So anyway, let me just put a theorem / definition. So it's a theorem that you can take as a definition if you want. So let's just put it quickly here. So, okay, let me say it orally. So if you have a product, infinite product of something, let's call them ANs or BNs, then this is said to be convergent if the partial sums converge to some finite number. Okay, the partial products, sorry, converge to a finite number, but excluding possibly a finite number of factors. So you may have to remove a finite number of factors that are 0, and then the product converges to a finite number. And then you're happy, because you would be very unhappy with your definition if 1, 0 would ruin everything. Right? So this, and usually you write an infinite product on this form, by the way, because then the convergence is related to this AN going to 0. Right? So this infinite product, like this. So assuming that none of these, that we have removed already, maybe a finite number of factors that are 0, so this is said to converge. So this converges if and only if some sum converges. And what sum should this be? There's only one natural thing, right? The sum of log, exactly. So the infinite sum of the logarithm of 1 plus an converges. And now this is the logarithm of complex numbers. So where log is any branch, but where log is the principal branch, of the logarithm. Okay, so this is what it means to converge, and there is also a very useful theorem that gives an alternative formulation of what it means for a product, infinite product, to converge.
Why did we add the 1?
Yeah, so this is for psychological reasons, right? Because you know when you have a sum of an, then if an is close to 0, then this is usually a nice thing, right, for convergence. So here we want to write it like this, and then an close to 0 is nice for convergence. You know, it's just psychological. It's nothing, yeah. But you usually write it like that. It's kind of. So you also have this, that the product of 1 plus an converges if and only if the sum of the absolute value of an's converges. Okay, so this you should also know. Slight intermezzo. And now I am on the final page of the whole course. So I know I'm slightly over time, but one page left, okay? So now, okay, so let me actually proof of the product development. So that way I will at least have done something. This you can understand. The relationship between the zeta function and the primes is the following. That, okay, first of all we have the convergence. So this product of 1 over 1 minus Pn to the power s. So this converges now if and only if the sum of absolute value of 1 over Pn to the s, if this converges, okay? And when does this converge? So this is okay if the real part of s is greater than 1, clearly, because this is a sum of, so it's 1 over the primes to the power s. And this is smaller than or equal to 1 over n for every natural number, because the primes is a subset of the natural numbers, right? Okay? Which is equal to the sum of 1 over n to the sigma, which is less than or equal to, and this is sigma, right? So if sigma is greater than 1, then this converges. Now, assuming that sigma is larger than 1.
Excuse me, before you rise.
Yes.
Is it important the word ascending?
You,
I mean, can we shuffle the term? Or it's important in the product?
Well, for sure you can shuffle at least a finite number of terms. Apart from that, I don't know if there's a subtlety, but
I think it's okay to shuffle because if we have an absolute convergence with about series, then we can shuffle without a problem.
Yeah, so if sigma is larger than some sigma 0, which is larger than 1, then you can probably shuffle. But, okay, I'm very far from an expert on infinite products, to be honest. Okay. Okay, so now comes the trick. So assuming that this sigma is larger than 1, then you can do the following. So you can look at the zeta function times 1 over, and then you take the first term here, okay? So 1 over 2 to the power minus s. Okay, so we wanted to show that the zeta function was equal to the infinite product of all this stuff. So now we take the first prime, so this is the first factor in our infinite product. And we say that if I take this function times this, then what is it equal to? Okay, so this was equal to, because sigma is larger than 1, this was equal to the infinite sum of n to minus s. Okay? So this is equal to sum n to minus s minus sum of 2n to the minus s. Okay? So this is equal to actually the sum of n to the minus s, where n is what? All the odd m's, right? So 2 does not divide n. Alright, because, okay, so n goes from 1 to infinity here. N goes from 1 to infinity here. So here they cancel each other out whenever n is an even thing. So what's left are the odd ones. Okay, so in the same way, I can do, now if I take 1 minus 2 to the minus s times 1 minus 3 to the minus s, I take the next, it's not the next number, it's the next prime, okay? So, which happens to be the next integer. So this is equal to the sum of n to the minus s, where 2, so 2 does not divide m,
And 3 don't.
and 3 does not divide m. Exactly. So I have this. And then, in the end, so more generally, you have that if I take this times the infinite product of, times some partial product, like this, to make sense of it, of 1 minus Pn to the minus s, then you see that this is equal to the sum over, sum of m to minus s, where 2 does not divide m, etc., and Pn does not divide m. Okay? And what is the limit of this as n tends to, big N tends to plus infinity? It goes to 1. So this goes to 1. Because we first, of course, the next term is Pn plus 1 to power minus s. Okay, so this goes to 1. And this ends the proof, right? So therefore, since this tends to 1, we have shown that actually the zeta function has to be equal to, 1 over the zeta function is equal to that product in the limit. Okay, and now, so we see that the product, now we come to the product development. What does it imply? So it implies that this zeta function has no zeros in s equals minus 2, minus 4, minus 6, and so, sorry. No zeros in the real part of s greater than 1. Okay? This is what I want to say. And we recall that we had the trivial zeros in s equals minus 2, minus 4, minus 6. Okay? So this is what we know. And now the question is, so where are the non-trivial zeros? Because there are more zeros of the zeta function. And this is exactly what the Riemann hypothesis is about. Okay, so the Riemann hypothesis. So this was Riemann in 1859. Okay, and it also, one should apparently also cite Enrico Bombieri for this, who's an Italian mathematician, Fields medalist in 1974. So he was until last year, 2018, he was the only Italian Fields medalist. Until now, also we got Alessio Figali, who won in 2018. So he won it in 1974, Enrico Bombieri, so you should know his name, since we're in Italy now in particular. And, okay, so the Riemann hypothesis, which is the Hilbert's 8th problem, I should also write this. So do you know about this list of problems? So Hilbert's 8th problem. And it is a Millennium Prize problem. Okay? Along with 6 other problems. It's a Millennium Prize problem that will give you $1 million if you solve it. Okay? And Hilbert's problems, this was in the year 1900, mathematicians gathered and they made a list of all the important problems they wanted to solve in the coming century.
20.
Yes, and many of them they did solve, but not all of them. And Hilbert's 8th problem was the Riemann hypothesis. And
How much they solved?
this is still open.
How much of problems they already solved from 20?
That's a good question. I don't have a number like that in my head. We solved some are unsolved, basically. And yeah, we put the Millennium Prize.
I just want to solve Hilbert problem.
Sorry?
I mean, there is a kind of recompense for solving one of the Hilbert problems.
Yeah, I'm not sure about the prize money for that, but I think they made the most prestigious ones Millennium problems, basically, like P versus NP, Poincaré conjecture, which is now solved, was a Millennium problem. Yeah, I actually have a list because I anticipated this question. So, have Young-Mills and mass gap problem, Riemann hypothesis, P versus NP, Navier-Stokes. But if you solve Navier-Stokes, we can throw all the computers in the C and we can predict the Weber without computers. Okay, then we have Hodge conjecture, which is close to my field. Then we have Poincaré conjecture, which was solved. And then we have the Birk and the Swinnerton Dyer conjecture. Sorry? Young-Mills and mass gap problem.
Yeah.
Yeah.
And the Navier-Stokes stability.
Yeah, Navier-Stokes is a PDE problem.
Yeah.
So then you have, so I haven't written it down yet. So what is this famous Riemann hypothesis? And then I'll end. So the Riemann conjecture or Riemann hypothesis is that all non-trivial zeros, so meaning the ones I have not already listed, so all these ones of this meromorphic function lie on the so-called critical line real part of S is equal to 1/2. Okay, so this is the Riemann hypothesis. Looks like, as all of these famous conjectures, it looks like sort of nothing, right? Looks like a homework problem. But it's not. So if you go on Wikipedia, so again, I'm not a number theorist at all. So this is complex analysis meets number theory. But if you go to, say, go online, go to Google, then you will find this enormous list of problems that follow from the Riemann hypothesis in number theory. So what people did is that they couldn't solve the Riemann hypothesis. But people started doing this. They said, okay, assume the Riemann hypothesis is true. Then what can I prove as a consequence? And then they could prove all sorts of things. So basically you have this, nowadays, this huge mass of knowledge that if the Riemann hypothesis is true, then this, that. So we have a huge number of theorems that depend on the Riemann hypothesis being true. And we really think it's true because you can check, with computers, try and approximate zeros, using the argument principle, etc., do many other things to see if it seems plausible, and it seems to be true. But until we have a solid proof of this, all of this is somehow hanging in the air, all of these number theory results. So if you prove this, automatically you put the last fundamental stone to prove probably thousands of other results immediately in number theory. So this is one of the reasons why this is so extremely important. I mean, all these people have proven results assuming this, and they're all very worried and hope that soon someone will solve this so that their discoveries are actually theorems, and that they know are true, not just an implication of something that may or may not be true. Okay, so I am well over time. I'll be happy to take some questions, but I'll stop the video.